what I'm going to do is review what we covered last week. And what we covered last week is vertical displacement efficiency, but only in one layer. And one layer is not very useful, okay, because we usually have multiple layers, but it's a starting point, and we'll use the solution for the case where we have multi-layers. And what we had is that you had fluid 2, which let's say is oil, and it's being displaced by fluid 1, which is some sort of aqueous solution. Maybe it's water. And so that water is pushing the oil, fluid 1 is pushing fluid 2, from the injector towards the producer. And some of the things that we might want to know is what is the position of that front, right? The interface between fluid 1 and fluid 2. So we might want to know that position. We might want to know the total flow rate through there. The total flow rate is going to be constant, right? This is a 1D flood. We're going to assume incompressible, so the velocity is going to be the same at all locations. We'll want to know the vertical sweep efficiency, which is really the front position divided by the length. And we might want to know the pressure drop across this reservoir. Okay, what does the pressure versus distance look like? Now, what we did on Friday and what we're going to do again includes a lot of math. You know, and those are important for making predictive calculations. If I were to give you a homework problem, which I don't have time for, then I would have asked you to code this up in Excel or Python and to make some plots of pressures and make them, or you know, sweep efficiency and things like that. Okay, it's possible on a final exam I could have you do a very simple calculation, but what's even more important to me is the qualitative behavior. Okay, and the qualitative results are going to agree with the quantitative equations, but it's more important to me that you understand qualitatively what's happening and to be able to draw sketches, schematics, and plots like that. And we might even do some of that today and later this week. Okay, but mathematically, what we know is that the Darcy velocity is proportional to pressure gradient by Darcy's law, right? And because this is multi-phase flow, I've got to include my relative permeabilities. Okay, I put those in blue because I left them out in the original slides. I'm going to correct that on Canvas. But that's Darcy's law. And I told you the velocity is the same everywhere. So it's the same in fluid 1 and in fluid 2. In fluid 1, we've got water, so we'll use the water viscosity and the water relative permeability, and the pressure drop is the pressure at the injection well, P naught, minus the pressure of the interface, divided by the distance from the injector well to the interface, which is XF. But you could equivalently write Darcy's law for the oil phase, right? So we use the oil viscosity. This distance is L minus XF, and it's P prime minus the pressure at the producer well, which I called PL here. Maybe we called it P1 in our notes the other day. Okay, so these are both true statements, and we can set them equal to each other and solve for the interface pressure. If you do that, you get an equation that looks like this. It's just algebra. Okay, yeah, it looks ugly and all that, but the point is it depends on the viscosities of the fluids, the relative permeabilities of the fluids, and that front position XF. You could plug P prime back into either one of these equations. Okay, if you do it for, if you plug that back into Darcy's law, what you get is an equation like this. Okay, or if we write it in terms of the endpoint mobility ratio, you get this final equation over here. Okay, so this is the velocity versus pressure gradient. Now, if XF were 0, then it's all fluid 2, and then you get Darcy's law for the oil phase. If XF is equal to L, then it's all fluid 1, and it simplifies. But if something in particular, it's something in between. This is effectively resistances in series, right? So this is equivalent to if you've taken an electrical engineering class and you had resistors in series and you're trying to calculate current, or if this was flow through two pipes of different resistance, it's the same idea. And you get this solution over here for velocity. Okay, so for a given pressure drop, the velocity is going to change depending on where this location is. Only way it wouldn't is if the mobility ratio was exactly 1. Okay. Now, again, I keep on talking about how it's more important you understand qualitatively what's happening. So let's think about what qualitatively happens here. So for a constant pressure drop, if you were to replace the oil phase with a less viscous water phase, then the overall resistance will change with time, so I expect the velocity to increase with time. If I replace the oil phase with a more viscous phase, let's say it's a viscous polymer solution, then it'll get harder to flow as I inject more and more polymer, and the velocity will decrease with time. And that's what I say over here. Okay, you can show that mathematically, but it also makes sort of common sense. Okay, so talk about vertical sweep efficiency. One thing is that we said we're interested in the pressure profiles. So the pressure is a function of distance. And again, here's my one layer. I've got my aqueous phase and my oil phase over here. The pressures are going to decrease linearly within a phase. It's just given by Darcy's law, right? We know that pressure is going to decrease linearly for a constant velocity. And so the pressure is going to decrease from P naught to P prime, and then from P prime to L. Now the slopes of these are going to be different. The slopes are going to be different depending on what the ratio of relative permeabilities and viscosities is. That is the mobility ratio. So if fluid 1 is less viscous than fluid 2, the slope is going to be higher here than it is over here. Okay, it's going to have a less resistance there than over there. Alternatively, if the endpoint mobility ratio is less than 1, think of that as being that the aqueous water or polymer phase is more viscous than the oil, then you're going to have a steep pressure drop until the interface and then not as steep until the end. Importantly, the pressure is going to equal to P0 and PL, the two edges. Okay, and we just derived this P prime over here, right? So again, you can mathematically plot these, right? I could give you a position XF, I could give you an endpoint mobility ratio, those types of things, and then you could plot it up. I might ask you, what I'm more likely to ask you to do on a final exam is to sketch it to where there's not an exact right answer, but there's qualitatively a right answer, which is what I'd be looking for. Okay, so how does this front move with time? Right, the front is this position where fluid 1 is an interface with fluid number 2, and how does that change? Well, we can do that, we can figure that out through a mass balance. Okay, and all this says the change in mass with time is going to be given by this rate. Okay, U is Darcy's law, Q is the flow rate. The area is constant, you can pull that out and it cancels with A. And then the porosity and the residual water saturation and residual oil saturation are constant, so they can come out. So then you're left with this differential equation, which looks like this. Okay. All this is constants, right? I think I'm missing a relative permeability of water here, but the point is that you have the change in front position with time is a constant times this over here. And because XF is what we're solving for, and this is down over here, it's a somewhat difficult differential equation to solve, but not too bad. Okay, you use separation of variables and you can calculate it. It's not too bad, and in fact, the solution looks like this. Okay, it's basically the quadratic formula. L is the length of the medium, m dot is mobility ratio, K mu, this is the viscosity of the water, this is the change in saturation. That's just 1 minus SWR minus SOR. Okay, I've got that written down over here as well. Delta P is the pressure drop. That's going to be an imposed pressure drop, delta P. And then T is the time. So this position changes with time, obviously. And depending on the mobility ratio, that position is going to speed up or slow down. Okay, so if you look at XF versus time and you plot this, it looks like this. Now, if m naught is equal to 1, and the mobility ratio is 1, that means I'm replacing oil with an equally mobile water, right? So nothing really special happens there. That position increases. It goes from 0 to L. Okay, it's going to be moving along over here, but it does so perfectly linearly. It doesn't change. But if the mobility ratio is greater than 1, then that position is going to accelerate. Okay, that would be if I'm displacing viscous oil with inviscous water. Then the resistance decreases and then this speeds up. But the mobility ratio is less than 1, then it slows down. Okay, so this is the front position with time. What about vertical sweep efficiency? That's what we're talking about. Well, vertical sweep efficiency is really simple. Okay, the definition is this front position divided by L. So we had an equation for front position, you just divide by L. It's effectively a normalized, so where XF can go from 0 to L, EI can only go from 0 to 1. Okay, and so the plot for vertical sweep efficiency looks exactly like XF did, except now my axes go from 0 to 1. Now there's something really interesting here about a single layer. At the same time, like T, the vertical sweep efficiency is much greater when you have a high mobility ratio than a low mobility ratio. And remember what a high mobility ratio means. Okay, it's the simplest way to think of it is that you have a low viscosity water displacing a high viscosity oil. So this seems to imply that to improve vertical sweep efficiency, you would want to inject a low viscosity fluid or a poor mobility ratio. We define a poor mobility ratio as being greater than 1, a good mobility ratio is less than 1. This is only true if you have a single layer. In reality, we're going to have multiple layers and then this changes. We can still use the equations we developed, but we'll apply them to more than one layer and then look at vertical sweep efficiency. And so this makes sense. If you only had one layer, if you replace this high resistant viscous oil with a lower viscosity fluid, then the overall resistance decreases with time. That makes sense. So that's why the vertical sweep efficiency sort of accelerates with time. But let's see what happens when we have multiple layers. And this is going to be new here. So when I say multiple layers, we could have 100 layers, we could have 10 layers. Let's keep it simple for now, and let's just say 2 layers. Okay, qualitatively it makes sense. And what I have is a layer on top and a layer on the bottom. And the layer on top has a higher permeability. I know that immediately because fluid 1 goes further than fluid 2, at least initially. So if the permeability of layer 1 is greater than layer 2, then that injected water phase wants to preferentially go to layer 1. That's the path of least resistance. Right? If you're driving down the interstate and there's 2 lanes and one of them is backed up but the other one's not, and you're going to go the one that's not backed up and you'll go faster. If you look at the pressure versus distance, you can again calculate all this with your equations and make plots, but qualitatively speaking, if you had layer 2, well, and this is for a high mobility ratio, then you're going to have low resistance up until the interface, and then more resistance, so the pressure gradient is going to be high. Layer number 1 is going to have this slope through up until this point. We got this low viscosity water, and then high viscosity oil is given by this slope over here. Okay, so one thing that you see, interestingly, is that the pressures cross. So for part of the time, layer 2 has a greater pressure than layer 1, but later on, layer 1 has a greater pressure than layer 2. One thing I want to emphasize is that we're talking about non-communicating layers right now. These layers don't communicate with each other, meaning that there's some sort of barrier between them that prevents what's called cross flow. So flow can't go from layer 1 to layer 2 or from layer 2 to layer number 1 in this analysis. Now at the very end, I'm going to talk about the other extreme where you do have cross flow. But right now there's no cross flow. And this is what the pressure field would look like. Now the front position, XF, is given by a differential equation just like we did in the previous slide, except now we can apply it for more than one layer. So I put dxfi where I is the layer. I could be equal to 1 or I equal to 2 in this case, or if you had 100 layers, I could be equal to 100. You could solve this differential equation analytically like we just did for each layer, or you could do it numerically. And the other thing that you can do is look at the percent of the flow that's in layer 1 versus layer 2, right? So QI, so the flow rate in layer 1 as a percentage of the entire flow rate, Q, is given by this. And where these equations come from, if you go back, they're just Darcy's law. Let's see if we can find it. Let's see. It's basically this equation, and some things cancel, right? So this was Darcy's law. This would be for one layer. So then you could say that the flow rate in one layer, in layer I, is given by here, and the sum of all the layers is the total flow rate, and that's the denominator. So this is how you say QI. If you wanted to divide by Q, that would give you the percent of the flow rate in layer I is given by this equation. And you could equivalently calculate the vertical sweep efficiency, which is related to the position of each one of the layers. So n is equal to 1 to the total number of layers. I've also got porosity thickness and delta S. They could be different in each of the layers, and that's what complicates this. But if they were the same, then it would just be, you know, XFN over over 1. So that's how you would calculate that. So let's say we have two layers. We're flowing, we're injecting some sort of water phase to displace the oil. The permeability, K1, is equal to 4, and K2 is equal to 1. Okay, and initially this is saturated with the oil phase, maybe your residual irreducible water saturation, but you know, and so K1 is 4 times that. Maybe it's 40 millidarcies versus 10 millidarcies or something. Okay, so, and I don't want you to use any of the equations on the PowerPoint notes. Okay, this is all sort of common sense, just trying to think things through. Also, some of the answers I have are going to be on the slides that I haven't shown yet, but I don't want you to look at those because I want you to try to think through this yourself. So we've got this, and my first question is, what is the percent of flow in layer 1 at time is equal to 0 or 0 plus? Right, so immediately after we start injecting fluid, what percent of the flow goes in layer 1 versus layer 2? Okay. Both of these have oil, and they have the same viscosity of oil. I'm injecting water of the same viscosity. You don't need to know what it is. You don't need to know what the mobility ratio is. What is the percent of the flow in layer 1 versus layer 2 after I start injecting? You could assume that these both have the same thickness, same porosity, same cross-sectional area. You could use the equation I gave you, but you don't need to. Let's just try to think things through what makes sense. So the answer is 80% of the flow goes in layer number 1 initially. It's 80% in layer 1, 20% in layer 2. Okay, why? Because permeability is 4 times greater in layer 1 than layer number 2. 4 times greater permeability means 4 times greater flow rate. 4 out of 5 is 80%. Now, it'd be a little bit more complicated if the thicknesses were different, the porosities were different, the areas were different, okay? But, you know, and that's why we have these equations that I showed you, but this is just sort of a back of the envelope quick calculation, right? So if all these are the same and you got a high permeability of 40 versus 10, 80% of the flow goes in layer 1. Okay, so then my next question is to plot, what do we want to look at here? So we'll look at Qi over Q, right? So this is what this was, Qi over Q versus time. I'm going to say the mobility ratio is 1. Okay, so what I want you to plot is Qi over Q for layer 1. Let's just do layer 1. Okay, so I can just put Q1 over Q. So this is, the y-axis is the percent of the flow in layer 1 versus time. And what we know is that a time is equal to 0, that it's 80%. So I'll just put that right there. I'll call this 0.8. Okay, maybe this is 1. So I want you to think about that. The endpoint mobility ratio is 1. How does this change, if at all, over time? So, remember what a mobility ratio of 1 means. It means that we're replacing the oil with an equally mobile water. So it doesn't change the ability to flow at all with time. Okay, as it doesn't matter if I've got 100% oil or 90% oil or 50% oil or 0% oil, it's being replaced by an equally mobile fluid. So in this case, it's never changed. The mobility ratio is exactly 1. This never changes. Let's think about the next case. B. Say the mobility ratio is now greater than 1. Let's say like 10. It doesn't really matter what the actual, if we were calculating this, we need to know the actual mobility ratio, but this is just sketches, right? So now we have a mobility ratio greater than 1. That means that the mobility of the injected water is greater than the mobility of the oil. Or another way of thinking about it, you have low viscosity water displacing high viscosity oil. Plot what that looks like. Now, at time is equal to 0, this is still the case, right? Question number 1 still applies. But what happens? As 80% of the flow is going into layer number 1 initially. 20% is going to layer number 2. So it's filling the top layer, the already high permeability or low resistance layer, with low viscosity water. So it's making it even less resistant. It's making it even easier to flow in layer number 1. So what happens is it does this. It goes up. And it'll never quite reach 1, but it might reach 99% or 99.9%. Okay, as time goes on. And that's a problem. That's a problem, right? Because, maybe at first that's a good thing. It looks like a good thing, right? It pushes the oil out in that top layer really quickly. And you get that oil and you're working in the field and everything looks great. All of a sudden, you just start producing a bunch of water. Because the water you injected now has reached the producer well. You've already produced the oil in the top layer and all your other layers. I mean, there's only one other layer here, but this could be 100 layers. All the other layers are being left behind because 99% or 99.9% of the flow is in that top layer. Nothing's happening in those other layers. And that's bad. Okay, and that's a common reservoir engineering problem we have. When we deal with heterogeneity, we talked about heterogeneity last week, probably talking about heterogeneity in your geostatistics class. Heterogeneity can be a problem because flow wants to preferentially go in the most permeable paths. And once it does that, once it breaks through, then you're in trouble because you're just producing mostly water and then those other layers are being left behind and you're stuck of what to do. Okay, so this was MO is equal to 1. This is MO is equal to 10, okay, or greater than 1. Let's look at the last case where M dot is less than 1. I don't know, maybe it's 0.1, it doesn't matter. This would be a case where you're injecting maybe a high viscosity polymer. This is an enhanced oil recovery approach. You're injecting a high viscosity fluid to displace the moderate viscosity oil. What effect does that have on things? So plot what that looks like. It's going to be really tricky. Try not to cheat and look at your PowerPoint notes. Think it's going to be really hard to figure out exactly what happens, but you might come close. So think about it. Think about what happens, especially before and after the fluid breaks through in the layer. So initially, it's still going to be 80%. Okay, so it still sees this first permeable layer and this less permeable layer in layer number 2. So in layer number 1, 80% is going to have 80% of the flow. But as I start filling it with high viscosity fluid, the resistance is going to increase. So then it's going to be harder to go in layer number 1 than it was before. It might still be easier than layer number 2, but it will be harder than it was. So it's going to decrease with time. I think it gets to about 50%, and then it gets to breakthrough. Okay, so hopefully you got that part right, where this decreases with time, and that's a good thing. That's a good thing because that means that we're equally sweeping our layers at this time in all there, okay? Or even at earlier times, and maybe it's not equal, but it's not 80% anymore, and it's certainly not 99.9%. It's doing a better job of distributing the injected fluid and then distributing what's being produced out. Now, unfortunately, what happens when you get to breakthrough is that if I go back to my picture up here, you know, I was injecting polymer and I got this front. Once the front reaches the edge, then injecting more polymer doesn't do anything because it's just injecting polymer and producing the polymer. So that is not going to change at all. And I'm also injecting polymer in the bottom one, but it hasn't reached the edge yet. And so the resistance in the bottom layer is decreasing while the one in the top is the same. So what that means is that this is going to increase again, but it'll never get above 80%. Okay. So you'll have some sort of plot that looks like this. This is exactly what we just did, right? So I told you the answer was on here, and I didn't want you to look at that, but this is the fraction of the rate into layer 1. If the mobility ratio is 1, it stays at 80% the whole time. If the mobility ratio is 10, it increases. Once it breaks through, you know, then it just is fairly steady, you know, and that might be 99% or 99.9% of the flow is in layer 1. But if you inject a high viscosity fluid, or you get the mobility ratio less than 1, then this decreases, gets down to 50%, which is ideal. I mean, that's what you'd really want, is for, you know, all the layers to be equally sweeping, and then they all break through at the same time. Okay, but even when it's 50%, fluid 1, okay, the fluid 1 in layer 1 has made it further than layer number 2, and eventually gets to breakthrough. Once it gets to breakthrough, injecting more polymer in layer 1 doesn't change the resistance at all, but you are injecting that polymer in layer number 2, and when you do that, that's this fraction of layer 1 then goes up again, but it goes back up to 80%. It doesn't go up to 100% or anything. Another plot we could make, I could have asked you to do this, is vertical sweep efficiency versus time, or dimensionless time. Now remember, we want a high vertical sweep efficiency, and not surprisingly, it's the highest, the mobility ratio is low, right? And that was because of the reasons over here, is that at the same time, let's say a value 2, instead of having 99% of the flow in there, then you've got considerably less that was in layer number 1. So it's sweeping all the layers good, and you get a high sweep efficiency. The mobility ratio is 1, then you get this. If the mobility ratio is 10, then you get very poor vertical sweep efficiency. Okay, so heterogeneity matters, and that's what we showed. We had 2 layers, they had different permeabilities, and so you had preferential flow in one or the other. here's a case where I had 10 layers, a Dijkstra-Parsons coefficient of 0.8. Remember, Dijkstra-Parsons coefficient is a measure of heterogeneity. 0 is perfectly homogeneous, 1 is perfectly infinitely heterogeneous. And now we got a mobility ratio of 10 again. So this is like my low viscosity water. And this is the front position versus time, right? And so a lot of variability. So in the high permeability layers, it goes very quickly and it reaches the exit quickly. And then in the low permeability layers, it's slower. Okay. And what I've done here is I made a plot of vertical sweep efficiency at a particular time. You have to do it at a particular time, right? Eventually, if you were to wait long enough, an infinite amount of time, the vertical sweep efficiency would be 1 everywhere. But if we look at a dimensionless time of 1, and we plot the vertical sweep efficiency from 1 to 0, and we do the Dijkstra-Parsons coefficient from 0 to 1, and we do some simulations, we do some calculations for different scenarios, we see what the effect of the Dijkstra-Parsons coefficient is. So in all cases, if a Dijkstra-Parsons coefficient is 0, that's perfectly homogeneous, you get 100% sweep efficiency after 1 pore volume injected. Doesn't matter. It doesn't matter what the mobility ratio is. If all the layers are the same permeability, then it all invades all equally, and it does that. On the other end, if we have a Dijkstra-Parsons coefficient of 1, then the vertical sweep efficiency is very low. And then in between, there's some sort of relationship there. But you could see that for the same Dijkstra-Parsons coefficient, let's say 0.6, the green, that's a mobility ratio of 0.1, is much better than the red, which is a mobility ratio of 10. Unfortunately, that didn't come out on the legend. But low mobility ratio is much better than high mobility ratio, all else being the same. Okay, and so I make a few points about that, but that is that sort of summarizes what we do, and you know, all this can come from the quantitative results, the math, but most of it we can understand qualitatively from just understanding basic engineering concepts. So with that, you all have an excellent rest of the day. Thank you.